So, welcome to another session of Smart Energy Distribution. Today will be the last day in the lecture. We have again 2 lectures today. And as I told you last time, I'm offering you to have a visit to the Energy Smart Home Lab and to the House of Living Labs. Do you want to see both? Do you want to visit both? Yes? Okay. So we would then meet around, like at the same time at 2 at the Energy Smart Home Lab. Do you know where the Energy Smart Home Lab is? You don't know where that is, then you have to put a map on the lecture area, on the website of the course, and tell you where that is. And so it is just close to the Gerzenhörsaal behind the Electrotechnical Institute. Behind the IEH Institute of Professor Leibfried. Maybe you know that one. So it is a small building, and then from there we can walk over to the FZI and have a look at the House of Living Labs. Okay, so we do that on the 14th of July. Then, as I said, that's the next Thursday that I'm available on the Thursday, and so there we can have the final of this course. Okay, so last time we looked again at smart home and energy management. We had looked at that already. I had shown you quite a few things. We had looked at the smart home scenario, like that's that's the house we will visit. So there's just another student coming. Could you please take also a form for evaluating the course? Thank you. And we have looked at those scenarios. I have shown you more things about it. Like last time, we looked at other things. We looked at had been further already. I showed you something, told you something about organic computing last time. Yes, about the generic observer controller architecture, which is part of the organic smart home architecture. And I told you something about ways of realizing all that. I showed you this view again of the organic smart home combination with the EE-bus. We looked at a generalization of that architecture, which actually could be extended over the complete network. So this was the slide where I showed you that we can actually extend it and include many different or group many different components into virtual objects and then manage them in a reasonable way, where this is just showing that in principle it is possible to use it. It does not mean that this is the only solution for energy management. There are many solutions around, and they could also be integrated into such a concept. We briefly looked at self-consumption, self-supply. I showed you the results of optimization, showed you the way we actually optimize in our organic smart home architecture, with the way of representing the sub-problems by having the bits that actually carry or indicate the number of decisions that we can make, then the evaluation function, which will provide the load profile of the device that has to be scheduled, and then the back transformation to actually get actions, construct or commands for the device that has to be scheduled there. And I showed you how that actually operates, that if we optimize it in our bit vectors, then take such a bit vector and evaluate it, but by using the evaluation functions, combine those evaluation functions into one large function and then have the evaluation of the complete vector and take the best one after a certain number of rounds, and then you get the final schedule. I also showed you a view of the House of Living Labs, and the ingredients of it, many different components which all can be monitored and also controlled to some extent, not all to the same extent. Some are more controllable than others, and that's one topic that here are all the like this was the electric infrastructure and the metering infrastructure, the thermal infrastructure, and then this problem of communication and interfaces. We have to make sure that we actually can communicate with devices in a reasonable way, and this is one of the topics we address in the FZI. I showed you the interface briefly, and then that was more or less what I told you about the organic smart home and the smart energy topics that we address at the FZI. And then I briefly showed you this architecture about the signals that are sent in, or that have been sent in the controller architecture of the Meridio project, where we actually had something similar to the traffic light model of the energy system, where we have green, yellow, and red phases characterizing the degree to which bottlenecks occur in the grid. And yeah, this has been outdated now. The exchange places for Newcastle, the deadline has passed for applying. I showed you something about other devices for smart homes which also address the energy topics, showed you these ambient devices, showed you the Nest approach. We looked at Plugwise, and then I showed you the energy cockpit from ENBW with a few screenshots, and the Stromradar, the energy radar of power radar of ENBW with a very fine-grained resolution. And then I briefly mentioned the battery topic, where like E3DC still is a battery which is quite expensive. So far it is not a business case really to use battery in your home, but it will be in the not too distant future. Definitely when Tesla will be shipping its batteries to Europe, then that will be a major decrease of prices. That was the smart home topics, and then we looked at the next chapter on smart metering and security. I showed you something about smart meter backgrounds, and yeah, showed you examples for data that is sent from smart meters. We looked at benefits of smart meters, looked at the role in a smart home. I showed you the profiles that you get from smart metering systems, in particular if you have a fine resolution, where you can tell exactly what people have been doing and what kind of devices they have been using. Different ways of looking at profiles of using devices. Like this was from the Energy Smart Home Lab. And then we looked at a few concerns that you have, or questions you can ask with respect to such a profile, just to show you that there's really a possibility to derive knowledge about the behavior of people, about the activities of people inside a house. And so you have to, or you should be aware of that and know how to deal with it. If you don't care, it's fine, as you don't care if you use your mobile phone. But if you care, you have to either not let data go out of your home or make some other arrangements. And some other arrangements was, for example, this protocol which was called the Smarter protocol, or Smart ER protocol. So the Smart protocol with exactness and robustness. And I showed you how that operated. There we used we were just grouping end consumers into arbitrary small groups. These groups would exchange data, would exchange numbers, and these numbers would be added on one side, subtracted on the other side. and that would lead to an obfuscated, a modified profile. If you modify the values that you measure actually, like in this case here the 7, you add other values to that which are subtracted on other measured values, then you can make sure that the profile that you send looks very different from the actual profile that was measured, but the sum of all the profiles still is the correct sum of the consumed powers. So the sum of the load profiles is not modified, only the individual's load profiles, and in that way you can guarantee privacy, and you just modify the private data, but the aggregated data still stays the same. This is the essential point of that method. And then we looked at privacy preserving energy visualization, where the point was that you only have the right to see an exact picture of the load while you have been in the building. Otherwise, you should not see actually what has happened. So you have to, if you visualize the data on some screen, you have to know who actually is, who actually has been present or who is wanting to have a look at that data, and then you have to modify the data appropriately. And then we get to the smart meter protection profile. I showed you the basic architecture of that. We have the gateway, and we have the local metrological network, and the home area network, and the wide area network. We have to make sure that there's no unwanted communication possible. For that, we had like different things which had to be guaranteed, or we had looked at threats that are addressed, and so if you are providing a smart meter and claim that the protection profile is implemented, you have to show that you can actually, or that you have considered all these different attacks, different threats, and are able to prevent those threats from harming your system. Okay, and then we had the security functionality. I showed a little bit about that. The wake-up service. Wake-up service is an important part because you have to make sure that you can actually initiate in some way to have a connection, but since only the smart meter gateway is allowed to actually set up a TCP connection or an HTTP connection or whatever, you have to be able to actually wake up the gateway such that it does actually establish a connection, and this is done over the wake-up service. That was more or less it here on the smart meter, and then I said we would like to look little bit on risks, safety, and security in more general settings, and we started to talk about the requirements with respect to safety and security. So we have to be sure that we can trust the security and safety of all components, that we can trust the actors, we can trust the transactions and also the systems. And then this is the first new slide today. So safety and security. In German, it is just one word, Sicherheit. In English, it is a distinction between safety and security. And what is it actually about? There are many different attributes that you can look at if you talk about safety and security of a system. So one thing, availability is an important part. Availability has to do something with safety. A service or system has to be available for the complete execution of a task or function. And so what can be a problem for that? If you have a hardware fault, if a system breaks down, the system should still be available. So a hardware fault can threaten the availability of a system. So in the energy system, usually we talk about N-1 redundancy. That means we can always tolerate that one component breaks down. So system crash, hardware faults, they are problems for availability. All of a sudden, the system is not available to perform an execution. Reliability means that a task should actually be executed effectively and correctly. So in general, if you send an email, you would like that your email actually is delivered to the recipient. If you perform, let's say, home banking, money transfer, you rely on that everything is executed correctly, that the tasks are effectively and correctly executed. So validity of tariff signals, also important. You would like to rely on that the information you get about the current cost of electricity actually is trustworthy, that is valid. Demand-side management should also be reliable, that it's executing its task effectively. So if a demand-side manager promises to shift load from one time to another, that actually should be done, and so it must be reliable. Confidentiality, the next topic which is important, protection of documents and communication from unauthorized access. You don't want others to see your private information. For example, smart meter data should not be available to everybody, but only to those who are authorized to get that. So privacy protection is here the important point. Non-repudiability, strange word. Non-repudiability means that if you send a message, you cannot deny that you have sent it, or a recipient cannot deny that the recipient actually has got the message. And this is important, that you can actually have something you can rely on, like if you take part in an auction, for example, you have sent it and the recipient has to or cannot successfully deny to have received that. And okay, integrity, the next important part is that, like the integrity of messages, the validity of information you send in electronic documents, so bids and auctions or contracts. You have some contract, and you have to you must make sure that this content of the contract is not modified by somebody else, that if two partners sign a document, both actually sign the same document and not different documents. You need ways of actually making sure that you can control or check whether a document has the correct content. Metering data should be protected in a way that you can check whether the content of a metering file is actually the real metering file. So sabotage is the typical attack against integrity, that somebody is modifying documents. Authentication is obvious. You have to you have to show that you have to prove that you actually are a certain person. So you check the identity of a partner in electronic communication. You have to do that in order to make sure that only those who are authorized can actually get access to a system, to some resource or whatever you have to protect. So this is something to protect yourself against espionage and sabotage. Nobody should get access to data who's not authorized to get that. And then the final thing here, traceability. Who has done when, what, to which document or resource? This is something which also has to be looked at. And traceability, like in the energy setting, has interesting aspects. One aspect is that you could say the utility company wants to trace the usage of energy in all the end consumer sites. That's one kind of traceability. You could also say that you as an end consumer have an interest in tracing your data. Who actually has received your data and what have they done to the to your data. So this is traceability of data that belongs to you, and you would like to be able to trace what actually has been happening to the data that left your house. This is something which is hard to actually guarantee that you can do that, but this is also an important part of traceability. Okay, so again, safety and security risks. What are the typical risks? One certainly is that you have unreliable programs, you have certain faults in the program, and you have to know that quite often you have faulty programs. You need a patch, but unreliable programs can lead to safety risks, that if a program is doing something which is not actually desired. So it may be that you have insufficient robustness against unexpected environmental conditions, undesired effects during execution, side effects which you don't want to get. So this is something you can suffer from by unreliable programs. There are unreliable operating systems, and you could always say, okay, I just buy reliable programs, I just buy reliable operating systems. We know that this is not possible. Every operating system has some vulnerabilities, and so maybe that there is some faulty file administration, backup methods don't work right, access rights maybe are not correct. System crashes may occur with loss of data, then you have unreliable execution of transactions which had been interrupted, and then you have unreliable hardware. Hardware is unreliable over time. Like hardware wears out. If you use some electronic device, then current is flowing through metal, and this leads to changes in the metal structure over time. And so you have to suffer from, or you have to take into account that there will be faults at some time. So you may have hard disk crashes, you may have memory faults, you may have transmission faults, and you have to deal with all those faults. So these are typical safety problems. And then unreliable employees. System administrator. The system administrator has access to everything. If he is unreliable, then you are really in problems. But these are the typical risks you have to address. And then you might be careless with respect to access protection. So one typical carelessness can be that your password is too simple or not made secret. Too simple passwords, you all know, names, dictionary entries, and so on, usually nowadays are not allowed. Careless handling of passwords are also known. Careless handling of secret keys for cryptographic methods. Like we have nice cryptographic methods where we have secret keys, secret personal keys, and we assume that if we know that a certain message has been signed with a private key, then the person has done it. But if the private key is not kept secret, then you only know that a key has been used, but then you don't anymore who has used that key. So you just have to be aware of these problems. And then certainly, as I just said, the secrecy of a key is essential, so you don't just write that information down, you don't make it accessible to others, and you have to choose appropriate passwords. This is all, I think it's more or less known to you. I hope so, that you are aware of all these topics. Let's just look at this one topic of passwords. You know that you should not use well-known names or character sequences. Some rules are at least 8 characters, or not letters only, no trivial word. The simplest thing is to just generate and memorize passwords by a defining phrase. So if you would take, for example, this here as a defining phrase, you could say, okay, this phrase here would stand for the password NWKNOCS. And you could, every day you could have a different letter, like take the first letter, the second letter, whatever. But it's very simple to remember in a phrase and derive a password from that. And this will usually lead to a name which is not in any dictionary, which is hard to actually be guessed in some way. So defining phrases are the best way of actually selecting passwords. And even if you write it down, if you write a phrase down somewhere, how should people know what your algorithm is to derive a password from that? So this is a simple thing to use. Obviously, you don't store passwords in shell scripts. Who of you is storing his passwords in the web browser? None of you is storing his passwords in the web browser. I'm doing it. So this is certainly a certain risk if you do that, because there may, like this, like the passwords are stored there in a secure way, but you never know. Yeah, and so if somebody tries to attack that, then you might run into problems. Or if you leave your laptop open and somebody else gets access to that, can use all your passwords. Okay. This is something which I don't like at all. Change your password regularly, because this leads to, like this is one of the typical policies that are enforced in many companies. But the problem is that the more often you have to change your passwords, the simpler your passwords will be. And so it does not make sense really, because it does not increase the security of the passwords. That you don't reuse an old password is obvious. Keep it secret. Immediate change the password, obviously. You don't display a password in plain text. That's also clear that you don't do that. And if you are designing a system and you have to protect against attempts to get access with invalid passwords, you have to make sure that after a few attempts, after a few wrong attempts, the access is blocked. And so with that username, you cannot get access again only by being unblocked by the system administrator. Typical ways of protecting access to a system. Okay, then there's espionage. A lot of espionage is around. We know that. Unauthorized access to internal data by all kinds of people, private people, official people, secret services, and so on. By competitors in the industry. They all do something like that. Secret services do that. CIA does it. We all know about that. This is nothing new. This has been known for decades, that CIA is actively spying on all the information that is there in electronic form. So there's a large number of supercomputers, thousands of employees in southern Germany for scanning and analyzing all electronic communication. And all electronic communication means email, fax, and so on. This is all well known. Yeah, so if politicians claim that they have not known things like that, this is ridiculous, because this is all well known. And actually, there have been these large radar, big ears, listening posts of the Cold War. They were directed to the Eastern Europe, and at the end of the Cold War, they were redirected such that they could better control all the communication in Germany, in Central Europe. So this is just something which is known, and so you must be aware of that and be careful in what you actually transmit, such that it is easily read by others. Then one important point is that espionage is done by unreliable employees. Insider attacks are the major attacks that are occurring, because the secrecy or the security policies inside a company are not as strict as from the outside. The estimated damage on German industry is in this figure of around 20 billion euros annually. So this is a figure that I took from press reports quite a few years ago. I don't think that this has changed, that this has been reduced. It's always in that range that information is transmitted to others, to other locations in unwanted ways, and then this has effects on chances to sell your products or whatever, or what other kind of information is leaked to others, to other companies, which can make profit themselves from that. So this is a difficult topic, but you just have to be aware of these things. Sabotage, another thing from the outside by denial of service attacks. What is denial of service attacks? You know that if we use TCP, we have here like the application layer, and then we have all our sockets, or all our ports to our applications, and if you just send requests to a server and trying to access all the different ports, then this system is kept busy, and it's just busy with trying to answer all these TCP requests, and it cannot do anything, any real work. That means it is just busy responding to this denial of service attack. Many requests to the system which is actually handling the connection between the transmission layer and the application layer, and so such a port scan can effectively block a system from doing reasonable work. And this can, like if you notice, oh, there's one node which is sending all these requests to the server, you could say, I just block this one node. But you can certainly also do something where this node here is sending information to all kinds of nodes, and they all send messages to that other server which is suffering from such an attack. That would be distributed. Distributed, abbreviated denial of service attack. Something which is even harder to fight against. Very typical thing, like our computing center is always actively fighting against denial of service attacks. This is something which is more or less standard. So this is overflowing the server with requests on all of its ports, as I said, and so it's no longer doing reasonable work. So you can get partial protection by a firewall, which is just trying to detect that this kind of request occurs and then can block it, but this is expensive. Trojan horses are different. Trojan horses, as you know, are programs which are actually getting inside a system and then listen to whatever is happening inside and send this information to the outside again. In particular, this is of interest if you have a Trojan horse in your laptop or in your computer and it listens to every signal on your keyboard, then it can get all the information on your passwords and things like that, which are not shown on the screen, but when you hit the keyboard, the keys on your keyboard, actually these signals can be listened by a Trojan horse and then they get all the information. So Trojan horses are also a dangerous attack. Viruses, you know about viruses, they modify code and then modify the way you can use your computer. And again, from the inside, there are all kinds of attacks possible. The problem is that you can actually download attacking software somewhere in the web, and then have easy ways of attacking other computers. It is, some people say that this is one of the favorite sports of some secretaries who try to do do something against another secretary which they don't like and things like that. Although maybe one should not say that, but this is something which has been reported, yeah, that all of a sudden in some office the computer broke down all the time, and it was shown that this was an attack by some other office which just didn't like that office. Yeah, things like that happen, and this is the problem of information and communication technology, that we can do many things with that, and most of it certainly is something which is very favorable for us, but there are all the bad things that can be done, and we have to be aware that like at the moment where we introduce information and communication technology to a large extent into other infrastructures, into the energy system, for example, we have to be aware that those problems can occur. And we have to do something against that. Okay. More insider attacks. Like more than 2/3 of all security relevant events are caused by employees. So I have told you, I think, already that there were people here from a Stadtwerke, a municipal utility, and they said that, oh, they are certainly in favor of building up or considering to build up some smart grid relevant technologies, introduce smart metering systems and so on, but the communication should be done in a private network, so they have to build the network and operate the network, and they would never rely the open internet connections because they are also insecure, and they were really convinced that it is sufficient to just have a physically separated network which is operated by that company, which then, just because it's operated by that company, will be safe. And this certainly is not true. You have to impose security measures to make sure that you are protected against security events that occur because of some employees which are misbehaving. So firewalls and so on, all these things to protect against attacks from the outside are important, but you also need more security policies to protect against internal risks. The question is, what kind of problems can occur? We can have some passive attacks where you don't see any direct manipulation, without any direct manipulation. It's just that somebody else is listening to what you are doing. If somebody can listen to what you are doing, like for example, notices that communication is sent between two persons, then you know that communication has been sent, and this might be a very important information that a message has been sent, even without knowing what the content is. But if you have some context information, you might know something, or you might be able to derive some information from that. Active attacks are that you manipulate the information, and it may be that you manipulate a system just by delaying a message. You're not modifying the message, you are just delaying the delivery of a message. If this message sends a bid to an auction, to delay a bid can have drastic consequences. And so certainly the manipulation or like to make changes on a document would also be a manipulation, but it's not the only one. So in order to use or falsify original data, this is an active attack. And then there can be system events that you have, the system component is manipulated by a third party or by the system itself. Maybe something is failing, and then some functions cannot be executed anymore, and you have system events which actually trigger attacks on your system. That goes more in the direction of safety. This here is definitely about security. What can you do against that? You can build a safe and secure architecture. only hire reliable employees, only use reliable programs. Certainly you could use all kinds of checks whether your program is reliable. You can prove that it does exactly the right thing, but it is not really possible to achieve that completely. And so you have to protect yourself against unreliable components, in particular here, for example, reliable hardware. You have to make sure that even if a system fails, you can still get the correct function. So a central server should be doubled or tripled. If you have two components running a certain program and you check the results, you check whether they are equal, then you notice if one of them is faulty, you notice a difference and you notice something is wrong. If you have three components, three identical components, then you can perform a voting on that. And if one of them is faulty, you still have two which are correct, and so you can just do a voting, and the result of the voting is the result of that function of those components. So this is like triple redundancy is a standard way of actually making sure that you can tolerate single faults. So one component can get faulty. Certainly if this component here gets faulty, the voter, then you have a problem. But assuming the voter is still correct, you can tolerate the faulty behavior or a crash of one of those components. In space missions, for example, we have five-fold redundancy very often. So we have 5 components which are used to actually perform one function, and you can tolerate up to 2 broken components, because then 3 of them will still be correct, and with a majority vote you can tolerate 2 faults. So this is standard there. Is this mine? Yes. Bad. Okay. So this is standard architectures, and there are many architectures using redundancy in this way. Like stock markets, for example, they are always running in with at least 2 parallel components in a tandem way, such to make sure that you have 100% availability, even if one of them has to be taken out for maintenance or whatsoever, the other one is still running. So this is just a standard way of making sure that you can tolerate typical faults in a system. And if you have a distributed system, you should always have multiple connections to be immune against link failures. And there have been examples where you had like many systems and they were connected in different ways, and you even had several, like multiple lines to make sure that you are safe against a faulty link. And then there was an example there was an event close to Frankfurt where they had some construction work or some work where they had to dig in the ground, and there was one machine there which just took just a bundle of cables, and it was torn apart, and this was having many redundant links between essential components. And so you have to make sure that those redundant links are actually far apart from each other, such that an event on one of the links will not influence the other links also. So redundancy is a key to having fault tolerance and more safety. And then if you want to protect against attacks, you can use firewalls. You restrict connections to port 80, just to HTTP requests. It is still possible to channel all kinds of attacks over HTML, over HTTP requests, but it's still much safer than having all the ports open. And so this may reduce the network performance, certainly. If you want to learn more about firewalls, you can look up that URL. Then one point is that you might still know the Java applets. I just recently heard that applets actually will be phased out, but what we still have is mobile code that is sent from some machine onto your machine, and in your machine you just build a sandbox, and so the external code will execute in that sandbox and can do whatever it likes there, but from that sandbox there's no connection to other resources in your machine. So the idea there is that an applet must not access local resources or establish connections to other systems unless you have a signature on that applet, a certificate that this applet is trustworthy. So signed applets may, so I should take that out again here and draw the sandbox somewhere else. So that was the sandbox here. You have the code, and it can do many things there, but it cannot access your essential resources locally. It cannot establish new connections to the outside world, and so it can just provide a certain service, but it cannot actually do something with your resources. And if you want to do something in a secure way such that nobody else can get access to or can get the information content of the data that they might get access to, then you need to use cryptographic methods, and I will tell you something also about cryptographic methods in a moment. Okay. So we can protect ourselves against passive attacks either by access control for files and transmission channels, which is always not completely possible, but it should be done. You should control the access, but in addition to that, what you should use is encryption, and it means that no unauthorized person may be able to retrieve original information from a message or a file. Even if you get access to the file, the content is hidden to you. Now it says here, no authorized person may be able, but what you really say is only at an expense that by far exceeds the value of this information. This is an important point. If the information is not that valuable, you would not invest very much in the methods to make it safe against attacks. But if it's very valuable information, you will make sure that even if you invest a lot of money, you will not get the content. And then we have to protect against, protection against and detection of active attacks can be done by authentication. Authentication means that I check whether a message or a request or a program which I'm receiving actually comes from a certain validated sender. And this can be done by checking whether a personal secret of this person has been used. It's interesting that there are currently quite a few things going on to modify standard ways of authentication. You know the simple way of authentication where you just use a username and a password. This is the simplest way of authentication. And then we have something like a signature with a secret key. And nowadays, like for example, our smartphones, they, like the operating systems there, the security parts there, now use things like finding out or checking whether this device is used in an unusual way. So by moving that around, I have certain ways of putting the smartphone always in my pocket here of my shirt, or others put it always in their trousers. And so you have different ways of actually using your phone, or you put it to your face and there's a camera in there. The camera can take a picture of your face and it notices how it looks like if you phone with a smartphone. And this is the information that now is combined with other kinds of information that the smartphone knows. And then this is used for authentication. So if you claim to be a person that owns this smartphone, the smartphone can check whether you are the person who always used that or not. And so this is a completely different way of checking whether it is actually real person, or whether you are allowed to use that. So far we just have the pins that we type in, but that's a very simple way of doing it, and it can be forged. So authentication, integrity checks is another point. We want to make sure that the data and the data flow have not been changed. And what I will tell you now in the next slides is how we can do that, how we can make sure that I can attach information to a document, for example, to the data that I sent from a smart meter, such that the recipient can check whether actually it's coming from my smart meter or a smart meter with a specific ID, and whether the data has been modified or not. And we can do that, check the integrity with respect to the sender information, the contents, ordering of data, timestamps, and so on. But it's an interesting area. Many things are happening there currently. So in order to be able to do that, we have to briefly look into cryptographic methods. I will not give you an overview of all cryptographic methods, just very few things. And so what are cryptographic methods about? These are methods used for encryption and for decryption. And the basic assumption is that these methods are publicly known. It does not make sense to say, oh, I have a very sophisticated method, an algorithm to hide information, and I don't tell you how that is done. It will not be a lasting secret. Somebody may get access to that, and then if you have the method, you get access. So the method has to be publicly known, and the security has to be based on some few parameters. These are the keys. That's the key information for cryptographic methods. So we have symmetric methods, where the two like senders, usually Alice and Bob, they have some secret information over there, some secret information over there, and you like if you send information here, this is encrypted using that secret information, and when it is received, it can be decrypted using that secret information. And in symmetric methods, this is the same secret information. Both need the same key. There's a range of different methods available. The first here is the data encryption standard, then several others. This here is the advanced encryption standard, which is now the most commonly used method. DES was the predecessor, and there are many other symmetric methods around. Asymmetric methods are different. Asymmetric methods have a secret key, a private key, and a public key, which sounds strange that I said secret parameters, and still we have a private key and a public key. I will show you in a moment why that can be reasonable. There are also many different systems around, Diffie-Hellman, Algamal, RSA, like all the names of people who have designed that. There are also the elliptic curves in combination with Diffie-Hellman quite often. So many different methods around. I will show you just very few. And encryption and decryption should not slow down communication, should be done on the fly very fast, but still secure. And certainly the costs of breaking the code should be larger than the value of the plaintext information. Obviously, if encryption means I use a certain key, certain information, 64 bits, for example, to encrypt a method or a message, and I need the same 64 bits to decrypt the message, I could just guess the 64 bits. Now the probability that I guess correctly is very low, but still I might be lucky and I get exactly the right key. This does not show that the code has been broken, or this method is unsecure all of a sudden. It just means that I have been lucky to just get the right, or to guess the right key, but I cannot, the next time on the next message, which has been encoded with a different key, I will not be able to just guess that again at with very little effort. So the expected costs of breaking the code must be very large. And it must be very difficult to actually get partial information about the plain text that is encrypted there. So, let me show you a very simple example, a symmetric stream cipher. This is like a stream or messages that we send, usually are messages of zeros and ones. So if we want to hide the information, then we can use such a symmetric stream cipher. We just generate a pseudo-random sequence of the same length as the plain text, again as a binary sequence. And then we just perform the XOR of the 2 bits always. Yeah, we just write here A XOR B. Now we have a ciphertext. If you don't know that random sequence, you have no idea what the original plaintext was. The nice thing about the XORing operation is that you can decrypt by just using the same sequence again and perform XORing, because A XOR B is always equal to A. And so the secret in this case is the random sequence. Since it is a pseudo-random sequence, you just need the seed for generating that sequence. This is what you have to know on both sides. You can generate a random sequence, and then you can very easily encrypt and get this ciphertext, and only the person who knows the correct seed for that random sequence can decrypt that. So this is very simple symmetric stream cipher where you encrypt the bits individually, like you take just one bit position and get the cipher symbol for that. So here, like this is something which is essentially inside the method RC4. The R usually stands for Rivest. Rivest is one of the scientists in that area. And then there are symmetric ciphers where there are block ciphers, and block ciphers are operating in a way that you have your message. You just chop it into blocks. For DES, it's 64-bit blocks, so 64 bits, and then you take this block and you encrypt that block by some ciphertext. This is done in a very sophisticated way, having 16 rounds of encryptions. And one important point certainly is that you always have to be able to reverse all these operations that you make on that encryption, or that you make on that ciphertext. But this is all possible. This has been a standard for quite a long time. 64-bit blocks are encrypted using 56-bit keys. Has been designed by IBM long time ago, 40 years ago, and in cooperation with the NSA. it is no longer assumed to be secure. Meanwhile, there are hardware devices which are actually capable to get the passwords or the not the passwords, the secret keys within something like 24 hours or even less at not a very large cost. Yes, I have a question. Yes. If, like you referred to the previous slide, yeah, in the previous slide, this is a good question. This is exactly the problem of the symmetric cryptographic methods. If you need the same secret information on both sides, you have to make sure that they both have the same information. So how do you exchange that? Maybe you have some method to find out from the newspaper, or there's a certain word on the... you can imagine all kinds of things how you agree on finding the same key. A simple method of doing that actually is to just select a random session key for sending one message, and then you encrypt your message, and you use an asymmetric encryption method to encrypt the session key, and you can send that message then to the recipient of that original message that you encrypted with the symmetric method, and there the recipient has his private key to decrypt the session key and can use that session key. So you need a secure way of transmitting the information on the symmetric key. Yeah, this is one essential point, and which is a vulnerability of the symmetric methods. The advantage of the symmetric methods is that usually they are they are not very complex, so they can be executed rather fast. So the overhead is not that large. Whereas for the public key methods, the overhead is quite large. There you have very high complexity, and so you wouldn't like to use the asymmetric methods on very large documents. But you can use them on rather short session keys for symmetric methods. And so it is this combination which you will see on one of the next slides, which actually is the way we deal with, or we communicate in a quite secure way meanwhile. So, symmetric methods. Data encryption standard is one of the standard methods. There's, like, DES is not recommended anymore. One method which you can still use is triple DES. This is, so it's a variant where you use 3 times DES in some sophisticated way, and there it is much more difficult to get a successful attack. Meanwhile, since it's 15 years ago, 14 years ago, we have a new method, the advanced encryption standard. The original name was the Rheindahl algorithm. That was an algorithm which was the winner of a large international contest on designing a new data encryption standard for symmetric methods. And you can download the code, you can download it in very different ways, different programming languages. This is a standard which is recommended to be used in communication. Triple DES, I just wrote it up there. So in triple DES, you have a multiple encryption with DES. There the key length is either 112 or 168 bits, so twice or 3 times as many bits as in the simple DES, where you just have 64 bits. So it is not exactly, no, here's 64-bit blocks, but 56-bit keys. So you have 2 of those keys for one version of triple DES, or 3 of those keys for another variant where you actually use 3 DES rounds with different keys. And then there are other examples, methods which are or have been developed in Europe and at Zurich. It's an algorithm or a method which is also widely available. It is available, for example, in the standard package Pretty Good Privacy. Who of you is using Pretty Good Privacy, PGP? None of you. Have never heard about PGP? PGP is open software, has been designed by some scientist in the United States, and it was at a time where there was a lot of discussion with the governments who said that they want to have control about encryption, about cryptographic methods, because only those who have criminal ideas will use cryptographic methods because they want to hide something. And so they said the state authorities would always need a copy of the private keys, of the secret keys. And it should not be allowed that people use cryptographic methods in a free way. In particular, strong cryptography should not be exported to other countries, meant to countries outside the United States, because that was a country where they really, or where they had designed strong cryptographic methods. And then there was Phil Zimmermann, who actually wrote up PGP, a system for using symmetric methods and asymmetric methods in combination to get secure communication for everybody. And he wrote the software for that, and he wrote a book where he documented the software. And it was not allowed at that time to export software, like essential software, to countries outside the US, but he definitely could sell books. And so he just sold his books, and Pretty Good Privacy got spread all over. Yeah. It just shows that if you try to restrict people from getting access to interesting information, just don't work. This doesn't work. People get access to that, and Pretty Good Privacy is a method which or a software package which is providing you with the capability to communicate in secure ways using typical protocols, but there's no state institution involved in that. You can build up your own web of trust, but the only problem is that since there is no state institution involved in that, it is not possible to have legally binding communication, legally binding contracts with something you'd use in Pretty Good Privacy, unless you include certificates from state institutions. So to have legally binding communication, it's not sufficient to use PGP. If you want to use that, you can just download it. It is available for free for private use. Okay, that's Pretty Good Privacy. Now, that was on symmetric methods, and now I want to explain to you a little bit about asymmetric encryption, public key crypto systems. Public key crypto systems looks a little bit strange, because what is secret if you have public keys? So here the idea is that every person has her own public key for encrypting confidential information. And to decrypt it, you need a secret key. And now, if you want to send something to some person, and you have many other people who want to send information, they can all use the public key to encrypt information, but only this person here has the secret key. They all have the public key. The secret key is only there, and only the recipient can decrypt the message. It's an ingenious idea. You just encrypt something, you can put it or make it publicly known that this is your public key, and then everybody can send you secret information, confidential information, by using that public key. So you have a message, you encrypt it using the public key, and then it is decrypted again using the secret key, and you get something back which certainly should be the original message again. So this is the requirement. Actually, you also have the requirement that M equals also P of S of M. Not just one way around, but it doesn't matter whether you use first the secret key and then the public key, or first the public key and then the secret key. The latter here, to first use this secret key and then use the public key, is of interest with respect to authentication, because then if this person here sends a message which is encrypted with the secret key, everybody else can check it, or check the validity, or can decrypt it with the private key, and so can check whether the secret key has been used. So this is one way of authentication. You know that only the secret key, or somebody must have used the secret key to write a certain message. You can check that by using the corresponding public key. Now, another requirement is that to retrieve the secret key from the public key should be as difficult as decrypting. Must be impossible to get the secret information. The secret information is the plaintext and also the secret key, certainly. As difficult as decrypting P of M without knowing S. Then S and P, both keys, should be generated in a very easy way. And encryption and decryption should not be too complex, because we don't want to have an overhead, a large overhead over our normal communication. And there are many standard methods. The Rives-Charmier-Edelman method, RSA, Diffie-Hellman-Elgamal. I will briefly give you an idea of what RSA is about, how that is working. And so here, what do we have in the RSA crypto system? We have a public key, which is a pair of integers, N and C. C stands for code, or encrypt. And a secret key is, again, a pair of integers, so the N is not the secret, the D is the secret. And this D stands for decode. And these C and D have at most as many bits as N, and N is a very large number. N is the product of two prime numbers. Okay, now you have N is a product of two prime numbers. You have the C and the D. If you are able to find out, like N is some product P times Q. If you are able to find out which two prime numbers are used to get that value N, which are the factors, then you can, and you know the public key, you can easily derive D. So the secrecy of that method depends on this question: which are the two factors of that number N? And this is a very difficult question, so the difficulty, the costs of decrypting in this case are equivalent to the cost of factoring a number. Now, if we have small numbers, it's no problem to find out which are the two factors. So these numbers usually are very large. Nowadays, we would always say you need at least 2048 bits for that, or even larger. You could take 4000, or usually we take powers of 2 as the number of bits there. And so very large numbers. And now what are we doing with those numbers? The encryption works in a way that we have our message, and we divide our message into sequences of numbers, bit blocks which are smaller than n. This n is the modulus. So we just take these values, and then we compute, like we take these numbers that are smaller than n and take them to the power c modulo n. Now, modulo n means we take the remainder by dividing that with n, and that is our encrypted message, that part CI. And the decryption works completely in a symmetric way. We take all those CIs, the C1 to CK, and then take the CI to the power D modulo n, and the claim is that this results in the same value mi. This holds true because of certain properties of numbers. This is based on results of number theory, and we can show that with an appropriate choice of C and D and n, this holds true. So the security relies on the complexity of factoring n, and one point certainly is obvious. This is a very complex operation, a very costly operation, because mi and c, ci and d are large numbers, having 2048 bits, for example, and usually in our computers we have 64-bit arithmetic. If you have a modern computer, maybe you only have a 32-bit arithmetic. That means when you multiply numbers, these are 32-bit numbers or 64-bit numbers, but not 2048-bit numbers. And so you need here multiple word arithmetic, and this is expensive. Multiplication of numbers, like if you have a k-word arithmetic, then it takes time order of k square for multiplying two numbers. Now, you want to not just multiply two numbers, you have to take mi to the power c, and c is a very large number. So you have to perform many multiplications. Actually, you have to perform many squarings of values. So you need the logarithm of c many operations, but the logarithm of c is in that range. It's the number of bits of that value. So it's many multiplications that you have to perform to encrypt and to decrypt. And so the RSA crypto system is a nice system, but it is very expensive. And so you don't use that on very long or very large messages. Okay, there are alternatives. So an essential or a good alternative is to use, as I said, elliptic curves. There you have there you have much smaller lengths of the keys with the same complexity. Another point is that I said in order to generate the keys, you need to have this number n, this product of large primes. So you need very large primes. How do you get very large primes? How do you know when you generate a certain number that that is a prime number? So this is again a difficult problem to find out whether a certain number is a prime. So you need primes having 1,000 bits, and for that we have randomized methods to actually check whether a number that we have selected randomly with 1,000 bits is a prime. And these methods are rather fast methods. So for that we need primality tests, and in principle primality tests are problems, or that is a problem which can be solved in polynomial time, but it is still very expensive. And with randomized algorithms for that, we get quite fast an answer whether a number is a prime or not. Okay, more details on that you can get in other courses. It's not the place in this course to actually do that. And the next would be how to use symmetric and asymmetric methods, but we do that after the break. It's 3:30, so we'll have a short break.